Built to look further back in time than any prior instrument, the James Webb Space Telescope has a specific mission: to observe the very first light in the early universe. But the data it recently returned challenges our current understanding of how the cosmos began. Pointing its infrared sensors at a patch of sky from when the universe was only their presence indicates the accepted timeline for galaxy formation contains a significant error, and we must investigate the era before these giants appeared to solve the mystery. This chart maps cosmic history, from the Big Bang on the left to the cosmic microwave background, a brilliant flash of radiation. To learn how massive galaxies formed so quickly, we must investigate this blank gap on the timeline, the era before the first stars. This gap is the cosmic dark ages. It is a period lasting hundreds of millions of years where absolutely no visible light existed. Instead of glowing stars, the universe was filled with a cold, expanding fog made almost entirely of neutral hydrogen gas. It was pitch black. This creates a severe forensic obstacle. We rely on capturing light to study deep space, but how do we investigate a period of history that is completely invisible? To see into that darkness, we must move away from the macro scale of deep space and look at the quantum mechanics operating inside that dark hydrogen fog. A neutral hydrogen atom is simple. It consists of one proton and one orbiting electron. In quantum mechanics, that electron has a property called spin, which describes its magnetic orientation, pointing either up or down relative to the proton. Occasionally, that electron will spontaneously flip its orientation to a lower energy state. When this spin flip happens, the atom releases a tiny pulse of energy. That energy pulse travels outward as an electromagnetic wave with a very specific signature. The distance from one peak of that wave to the next measures exactly 21 centimeters. A single atom's pulse is incredibly weak, but because the early universe was saturated with hydrogen gas, billions of these atoms were flipping at any given moment, combining their emissions into a massive, constant signal. The cosmic dark ages were never actually silent. The pitch-black fog was continuously broadcasting a faint, invisible frequency, and we finally have the tools to listen. But to hear it, we have to trace that signal's journey across 13 billion years of space toward Earth. As the 21-centimeter wave travels, it is affected by the expansion of the universe. This expansion stretches the wave, physically elongating its shape over billions of years. By the time it finally reaches our planet, that 21-centimeter signal has been stretched entirely out of its original band and into the radio spectrum. You can experience this yourself. If you turn on an old car radio and tune it between stations, a small percentage of that hissing static is this exact cosmic signal hitting the antenna. That everyday noise is actually a direct connection to the pre-stellar origins of the universe, washing over us every day. Because the signal arrives as radio waves, astronomers have to trade optical glass lenses for massive terrestrial radio arrays. Essentially, these arrays act like topographic scanners. By measuring the varying strengths of that stretched signal, they can map the exact density of the invisible hydrogen fog across the early universe. This map allows them to locate the cosmic dawn, the exact moment the first stars and supermassive black holes violently ignited within those dark clouds. The intense radiation from these early stars ripped electrons away from the surrounding hydrogen atoms. This created massive empty bubbles, or ionized zones, within the neutral hydrogen fog. Since ionized hydrogen doesn't emit the 21-centimeter signal, those bubbles appear as black, silent gaps on the radio map. By tracking these gaps, scientists can watch the universe's lights turn on for the first time. This ability to map the dark ages brings us back to the James Webb Space Telescope and its universe-breaker galaxies. The density variations recorded in the ancient hydrogen fog reveal the underlying invisible scaffolding of dark matter that predated the first stars. This dark matter scaffolding provided the gravitational strength to pull in enough gas to form those massive galaxies so early in cosmic history. The pitch-black, emptiest era of our universe is actually a direct broadcast of our origin story, and we have finally learned how to tune in.